Good morning. Welcome to the Baker Institute. We're going to go ahead and get started. I'd like to introduce Ambassador Derision, the director of the Baker Institute. He had a very distinguished career of public service in the Foreign Service and served as the Assistant Secretary of State for the Near Eastern Affairs. Also served as ambassador to Israel, ambassador to the Syrian Arab Republic, and has been the director of the Institute since its establishment 25 years ago. Let me turn it over to you.
Thank you very much, George. The reason I was ambassador to Syria and to Israel was I was the only schizophrenic in the State Department that could do the job. So. Well, good morning, ladies and gentlemen, and welcome to Rice University's Baker Institute for Public Policy. I'd like to extend a very warm welcome to all the attendees to this year's summit. It's truly remarkable that this is the 12th International Space Medicine Summit we have hosted here at the Baker Institute under the leadership of George Abbey, our Baker Institute Fellow on Space Policy. And we're very happy this year to be partnering with Texas A&M, College of Engineering, and Baylor College of Medicine. On this note, we would like to take a moment to recognize the late Dr. Bobby Alford, who formerly belonged to Baker College of Medicine. Bobby was one of the dedicated and visionary founders of this Space Medicine Summit, who unfortunately passed away this February. I particularly wish to welcome this morning our many distinguished guests visiting from around the world, including from the Space Station International Partners, the European Space Agency, Canada, Japan, and Russia. And we are likewise very happy to welcome guests from China. The landscape of space exploration is changing before our eyes. I don't have to tell this audience that. The reinstitution of the National Space Council and President Trump's call to establish a space force as a new military branch, along with greater private sector involvement in aerospace technology, are some signs of this. This summit, accordingly, is thus quite timely, not to mention the fact that this week marks the 50th anniversary of the successful completion of Apollo 7's historic mission. We are honored to count Walt Cunningham. Was Walt here? I hope. Walt, God bless you. The last living member of this mission among our panelists for this conference. But beyond these developments, strong international collaboration in space travel remains ever crucial, especially at this time of international discord in the body politic, not only domestically, but internationally. Without it, the International Space Center would not be flying today. The station has become the model for how countries, nations, people can work together to achieve common goals which benefit all and continues to provide the foundation for human exploration of space. Strengthening international connections and communications on a scientific and diplomatic level are therefore central to the aims of the Space Medicine Summit. So for the past 8 years, the Baker Institute has also sponsored a student exchange program with Bauman Moscow State Technical University in Russia, sending American university students to Bauman and welcoming Russian students to Texas to better understand space policy. This summit aims to further this cross-national educational mission. So ultimately, the road to human exploration of space begins with international cooperation and understanding of the effects of long-duration spaceflight on the human body. Just as President Kennedy articulated his vision for exploring space here in Rice in 1962, your deliberations here at the International Space Medicine Summit will impact the future of space travel and also have a meaningful impact here on Earth. So I wish you every success in your proceedings over these next 3 days. So it's now my pleasure to introduce George Abbey, whose a book has just come out, a biography on George Abbey. So I'm going to be his PR agent here. It's a must-read. But what really gets me is the notation on the back. One of the most elusive and controversial figures in NASA's history, George Abbey was called by those within the agency, quote, the Dark Lord, quote, the Godfather, quote, this is the one I love, the UNO, short for Unidentified NASA Official. So join me in welcoming the unidentified NASA official to the podium.
You can't believe everything you read, so. But I just want to reiterate what the ambassador said to welcome you all here. We're very pleased to have you here. You'll see on your badges there was a letter designation. That's for our group discussions. We have 3 groups, A, B, and C, and you can look at the program and find out what those groups are. So we put down a group that we thought you would be interested in, but you have certainly, you can choose to associate with any of the 3 groups. You have transportation over to the hotels, and I think that's all been arranged, and we have a departure time and each evening going from here to the hotels. And I have also co-hosts here in the for the summit. This time is the Baker College of Medicine. Jeff Sutton. Let me introduce Jeff. Jeff, where are you? There you are.
Well, thank you very much, George. And on behalf of the organizing committee, I'd like to welcome you to ISMS 2018. Thank you very much, Ambassador Dirigian, for your eloquent remarks, as always, and for allowing us once again to have the ISMS meeting here in this beautiful and inspirational setting of your institute, and very much appreciate your remarks about the late Dr. Bobby Alford. Dr. Alford was an amazing man. Professionally, he was a distinguished surgeon. He was a dean of medicine and chancellor at Baylor College of Medicine and a devoted educator. He was also the chairman of the board of the National Space Biomedical Research Institute, and he loved ISMS. He enjoyed very much the collegiality, the emphasis on international cooperation and collaboration, and the pursuit of excellence in advancing topics that were important to space medicine. We'll miss him very much, but we're also very appreciative of the legacy that he helped build with Mr. Abbey and others that allow us to be here today at this meeting. The panels and other agenda items are very interesting. Of course, the heart and soul of the meeting are the discussions that take place, the sharing of new knowledge, of experiences, and of ideas. It's always very enjoyable, and I'd like to thank you for taking time from your busy schedules to participate in this meeting and extend a very warm and special welcome to our out-of-town guests, particularly those who traveled internationally. I hope for everyone here has an enjoyable and productive meeting. It's now my pleasure to introduce Dr. Bonnie Dunbar, who's a veteran astronaut of 5 shuttle flights and currently holds the Tease Distinguished Professorship in Aerospace Engineering at Texas A&M University. Bonnie?
Well, good morning, and on behalf of Texas A&M University, welcome to the summit as well. I bring greetings from our Chancellor, John Sharp, who, and as I will quote from the remarks he gave earlier this year to the Academy of Medicine, Engineering, and Science of Texas, Texas A&M would like to be a preeminent university in space exploration, engineering, and science. Also bring the greetings from our Dean, Kathy Banks, as well as our department chair, Rodney Bowersox. We are interested in and have been part of space exploration through the Johnson Space Center and our graduates for generations, but we want to be part of this new frontier of returning to the moon and going on to Mars. So we're very pleased and proud to be part of this summit and a sponsor. Thank you.
It's now my pleasure to welcome to the podium, not an unknown official, but our very well-known president of Rice University, David Liebran.
Thank you, Ed. Good morning. I want to add my welcome to all the attendees of the 12th Annual International Space Medicine Summit. Over its 12-year history, the summit has certainly become one of the world's premier space medicine events. Especially want to welcome attendees from Canada, Europe, Japan, Russia, and the United Kingdom. And once again, the representatives from China, Dr. Wu and Dr. Wang. It's a pleasure to have you with us again this morning. I also want to add my special thanks to Texas A&M University College of Engineering in joining with the Baker Institute as a co-host of the summit. Texas A&M University's involvement as a premier aerospace engineering school contributes substantially to maintaining the quality of the summit's proceedings and the interchanges with the summit's attendees. Texas A&M has indeed been well represented in our nation's space endeavors and has made significant contributions by providing astronauts, engineers, and scientists to the U.S. human space program at every level since the beginning. And I'm particularly pleased that the summit attendees now include a substantial number of Texas A&M University aerospace students. Their involvement will help us ensure a great future for human exploration of space. Just as nations have collaborated to explore space and learn from those explorations, so must also universities, and many of those are represented here today. And thanks, of course, especially to Baylor College of Medicine and Jeff Sutton, and a special thanks, as always, to the truly remarkable George Abbey and Baker Institute's Space Policy Program. I want a book like that written about me one day, too, with equally mysterious terms for me. 50 years ago this month saw the successful completion of the historic and critical first step leading to the accomplishment of the goal so eloquently proclaimed by President George Kennedy, not too far, think in that direction, from where we sit today at Rice University's football stadium, just 56 years ago this past September. In the famous words he uttered, quote, "We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, one we are unwilling to postpone." As I said, he made that speech right here on this campus, and certainly the subsequent history demonstrates the truth of what he said in terms of the program organizing our energies, not just here in the United States, but around the globe. 6 years after that speech, the critical first step was completed with the successful flight of the first manned Apollo mission, Apollo 7, 50 years ago this month. And we are so honored to have a member of that historic flight with us here this morning, Walter Cunningham. That flight enabled man's first venture beyond Earth orbit to the moon 2 months later, Apollo 8, and the steps that followed, leading to the successful landing on the moon by Apollo 11 in July of 1969. Like so many, I can remember exactly where I was at that moment. I was on a field in Idaho with a bunch of Boy Scouts, and somehow they had figured out in this big field how to link up a bunch of televisions so that we could watch the first man set foot on the moon. Astronaut Neil Armstrong made the point of saying as he set foot on the moon that it was a small step for a man, one giant leap for mankind, implicitly emphasizing that space exploration was indeed a venture for all humanity. As we meet here this morning, the International Space Station, the focus of this meeting is flying overhead, a credit to the partnership that has been formed between the United States, Canada, Europe, Japan, and Russia. In his speech at Rice, President Kennedy spoke of international cooperation. He said, "There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to all. Its conquest deserves the best of all mankind, and its opportunity for peaceful cooperation may never come again." A year later, in September of 1963, in an address to the United Nations, he proclaimed, quote, "Finally, in a field where the United States and the Soviet Union have a special capacity, in the field of space, there is room for new cooperation, for further joint efforts in the regulation and exploration of space. I include among these possibilities a joint expedition to the moon. Surely," he said, "we should explore whether the scientists and astronauts of our two countries, indeed all the world, cannot work together in the conquest of space, sending someday in this decade to the moon not the representatives of a single nation, but the representatives of all of our countries." I certainly believe that one of the greatest accomplishments that we have seen in space over the 50 years since the historic Apollo 7 flight has been the realization of the international cooperation envisioned by President Kennedy as exemplified by the International Space Station. Today, a panel will meet to discuss the further human exploration of the moon. I would certainly commend to them the words just quoted that were spoken by President Kennedy in his speech to the United Nations Assembly 45 years ago. The human conquest of space has evolved from a competition between two superpowers to a program of international cooperation with many nations working together for their common good, building and operating an international space station. Those proven partnerships should be, indeed, the foundation for the human exploration of the moon and the further conquest of space. And the partnership should be certainly expanded to include the participation of other spacefaring nations, such as China and India and others interested. So I deeply appreciate the international character of the summit and hope that its deliberations and actions represent the spirit of moving forward together. And we're very grateful to all of you who have traveled here to participate, from as close as the Texas Medical Center and the University of Houston to as far away as Australia, China, Europe, India, Japan, and Russia. On behalf of Rice University, we wish you every success in your discussions and actions that may result from them, and thank you so very much for your participation at this summit here at Rice University's Baker Institute. Thank you.
Thank you very much. We'll go ahead and get started on our first panel. So let me get that first panel up here. And we're adding one name to the panel. Bill Shepard is also going to serve on the panel.
Why don't you sit here? Hey, Bill. How you doing? What's up? Nice to see you. Yeah, we'll grab it.
Okay. Great. Well, first of all, I know that President Lebron has departed the room, but wanted to thank him very much for his insightful remarks. The first panel is on maximizing the use of the International Space Station. The moderators are Don Pettit and Ola Kotov. Don is a chemical engineer and veteran astronaut of 2 long-duration ISS missions, Expedition 6 and Expedition 3031. He was also a mission specialist on SDS-126, and his cumulative time in space is more than 369 days. He's an avid inventor, innovator, and educator, not only in space but in extreme environments such as Antarctica. I understand you've gone hunting for meteorites down there. Oleg is a physician and a veteran cosmonaut who flew 3 long-duration ISS missions. He was a flight engineer on Expedition 15, and on Expedition 22-23, he became commander. On Expedition 37-38, he became an ISS commander for a second time. He's participated in 6 EVAs, and his total time in space is more than 526 days. So, Don?
We have a panel here to discuss maximizing the use of the International Space Station. And what I would like is to maximize the discussion between all you folks sitting there and these panelists here. So in that light, I'm going to do a quick introduction. I'll just read their names, and then I will allow everybody to speak for no more than like 3 minutes. So that way we could reserve the rest of the time for all this delightful discussion that I'm sure will happen between all you folks and the panelists. So let me read the names of the panelists here. We have Mike Barrett, and Bonnie Dunbar, Soichi Noguchi. We have Bill Pawlowski. We have Alex Polikarov. And then we have Julie Robinson. We also have someone that hasn't sat up here yet, Kate Rubens. You are listed on the list here, whether you knew it or not. There's an extra chair. And then Salajan Shaparov. Okay, so let's get on with it, and let's start off right here with Bill Shepard, who is also a late addition to the panel, and let everybody talk for a few minutes and then get on with the discussion.
Okay, well, I can give a little bit of background on the inception of the ISS program and some of the thinking that went into the strategy of how it was organized. In that the first several months of the space station's flight was going to have very limited communications with the ground. We had periods, some of which were in excess of 4 or 6 hours, without any telemetry being seen or any voice communication with Earth. And so the aspect of how the station's operations were organized, we felt was very much like a long expedition away from Earth to Mars. And the command and control and the responsibilities and authorities of the crew and the mission control stations on the ground was engineered with this in mind. The other aspect of the station that was very important to us was that it was operated as a single entity by a unified crew, where in extremis the crew was able to respond if they needed to by themselves to take care of the station and make sure that the safety of the crew was ensured. I can't speak factually about what the present organization of the station is, but what I detect in some of my interactions with people at NASA is we've gone to a very federated concept of operating today's ISS. And The crews do not spend as much time together. They don't have the same penetration into the systems and functionality of the other modules and segments from other countries on the station. I think this is fundamentally wrong, and I also think that it's not the model that we need to build on to go on lengthy explorations in the future. So I entertain any questions from the audience when we're done about this subject.
Oleg, a few words, пожалуйста.
Okay, with pleasure. Again, good to be here with you this time. And talking about utilization of station, about the increasing efficiency, is a question that we heard the last few years. Honestly saying, starting with utilization phase of ISS, when we start doing our operation by different segments, we understood that total efficiency of ISS is not good. And now we're open for discussion how to improve this science, how to get more results from the station as one aspect. And second aspect, we realize that somebody has to control or direct the science on ISS. Okay, the scientist, PIs is good, but every PI is really very interesting only in his own research and investigations, and sometimes it's not very useful for future space exploration. So in purpose to reach the moon or Mars or beyond, now it's 100% clear that somebody from agency or from officials, authorities has to control the direction for science. So we need to understand what we need to reach, why, when, and it's only way how we can fly to Mars. Okay, thanks.
Mike, a few words, please.
So I'm going to, I know there's a lot of people who are probably not as familiar with the inner workings of station. I'm going to probably go back about 50,000 feet to get a bigger view. The station was built as a huge laboratory. It's like the NIH, or maybe it's like the INIH, the International Institute of Health in Space. It's not meant to throw to Mars and explore there. It is meant to produce science, and yet it is a stepping stone to go to do these exploration missions that we want to do. And so with that, the mission of the ISS is inherently schizophrenic, if you will. We have healthy tensions that go on that I think, A, define us, and B, make us better. If you're talking about maximizing the use of station, I'd like to define what is the use of station. And the fact is, it means different things to different people. The currency of science is publications and utilization hours and various other things that are extremely important to an NIH mindset, but not very much so to a utilization mindset. And when you look at from a crew standpoint, where we are right now, the fact that you can just say, I need you to go spend 6 months in space and be extremely productive for many hours a day and then come back strong and fit. Okay, wow, we do that. That's routine now. The fact that we can operate and live day to day in space is just amazing. And it's an untangible output. It won't show up in utilization hours or publications. And the fact that we can do it internationally, I think, is amazing. A bit of a message more for the young people that seem to be clustered up there. If you ask us how we built station, just to skip to the end, we did it the hard way. If you were to say, I need you to build a laboratory that does all these NIH functions, and I want you to do it at least dual language, 2 languages to operate in. Let's make half English, let's make half metric, let's build a bunch of complicated modules, never fit check them on the ground, let's just launch them and hope for the best. And we did it that way, and it was hard, and it worked. And it probably worked better because we did it that way. And it shows the output of personal relationships and really sharp penciled math. Right? So that's where we are, and that's why we have the investment in station that we have today, aside from some of these other utilization metrics. The last comment I'll make is I did spend some time going back and look at crew comments. The crew always has a top 4, top 5 recommendations when they come back from station. And just like Dr. Kotov said, it's really oriented towards efficiency. The crew is really trying to work better, the best they can. You are working on somebody's science. There's millions of dollars and years of sweat and tears going into the project that's now down to you and your hands. And the pressure is really kind of high, and we take that really, really seriously. And so the crew's mind is in working as hard as they can. But I will share one comment that I found as I was going through these. And we also have an entrepreneurial wave that's coming to station, and it's kind of a fail early, fail fast mindset. Space is still dangerous. Our commute is somewhat more hazardous than those who drive to the NIH. And we've lost our brothers and sisters, both on the uphill and the downhill. And when you get up there and you get up and you do these experiments and you find a cable supposed to be, go into a socket, it doesn't reach because nobody fit checked it on the ground. Now, fail early, fail fast is okay, but when you're up there and you've risked that and your family has watched you risk that, wow, that changes your perspective on the mindset of quality. So that was a bit of an appeal, a bit of a cry for help, so to speak, from a crew member who remained anonymous in those comments. So fail early, fail fast, but do your homework on the ground.
Bonnie?
Well, thank you. So since we're increasing altitude, I'll go up to at least a 70,000 foot level. I had the opportunity in 1993 to be at NASA headquarters when we transitioned a U.S.-only station with international partners. It was an international station without Russia, and we redesigned it. It became what it is today on paper. It also went through a congressional vote, and we have a station, I believe, because we had a one-vote margin at that time or close to it. And in those discussions, if you read back, you'll see that we defined the station not just for science, but as an engineering platform, a platform to help us learn how to design for the future, going back to the moon and Mars. And so that's the context I'm going to frame my remarks in. We're planning to venture beyond Earth orbit. We're talking about long missions, and the long pole in the tent, one of them that we now recognize after 20 years on this station, is the Environmental Control and Life Support System. So from my perspective, and in reading the strategic plans where we talk about the crew-intensive work on ECLSS and the day-to-day operation of ECLSS and the failures that occur and the pieces that we change out, we're going to need a station in Earth orbit forever because technology is going to be changing. We can't test it in 1G. We have pumps that now fail less than 6 months that have to last 30 months. And so from an engineering point of view, perhaps we ought to be collaborating more, but also investing in more, because the science is wonderful. I've been part of the science, but if we don't have a laboratory or a station or a platform that's going to get us there safely, we're not going to be able to accomplish our mission.
Thank you, Bonnie. Soichi.
Good morning, Dobre Utra, 早上好. Good to meet the new friends from the wild east. I'll be very happy to join this distinguished guest panelist, and also very nice to see old friends here. Not that we are getting old, but we cherish the long-term friendship. Speaking of friendship, obviously I'd like to mention that International Space Station is based on the beautiful friendship, international friendship, US, Russia, Europe, Canada, Japan. And also we are expanding. Last month I was in Star City for my next space flight training, and we are happy to have UAE Space Agency coming into play. The Hadar and Sultan, both are very nice looking, very energetic, and nice person who is now in training for the upcoming mission. They bring us the new energy. They bring us a new idea, and that's what the International Space Station is designed for. And also for the utilization, it just keep moving. Last time I flew with Oleg Kotov 6 months together, and I think we're talking about the utilization time of a weekly, like 10 hours, 15 hours. And now I'm started training for next year, and they are talking about like 70 hours, 80 hours. So that's a huge jump. And we tend to think the International Space Station, now it's coming to a 20 years mark anniversary. kind of set in stone. No, it's keep evolving. It's keep changing. And this week I have all those informed consent briefing. All the topics changed a lot, and we talk about SANS, we talk about cognitive studies, probiotics, you name it, gene study also. So those things, it's the International Space Station never stop improving, and that definitely the theme of this maximizing use of the International Station today. Thank you so much.
Bill, a few words, please.
Sure. So I'm the token user on this panel. As the head of the Human Research Program at NASA, which has been around for about 12 years, we have the modest charge to identify all the health and performance risks for crew members that go to distances as far as Mars, and to figure out the right solutions and countermeasures for those things before we fly to Mars. So we spend a lot of time thinking about what the issues are for very long duration journeys. We work very closely with a lot of our international partners. In fact, I was with Oleg last week at International Space Life Sciences Working Group meeting in Rome, where we compare notes and look at the work that we're doing in our own countries and look for how we can work together. We have work on the ground together, U.S. Work that's going on in Germany, that's going on in Russia, it's going on in Antarctica, and our international partners are coming to the U.S. and working with us. We do a lot of work on the station together, joint studies with all the agencies that participate on the station. We start thinking about how much we've learned over the last 50 years in low Earth orbit. Most of that has been related to the gravitational effects and to the eclipse or the hostile closed environment. As we move on to these deep space missions, we have some new challenges that are going to be much more significant, I think, for the crew members. The radiation environment beyond the Van Allen belts, the extreme isolation and confinement, and the distance from Earth that doesn't allow you to return a crew member very quickly if you have a medical issue or something of that sort. Just the issues associated with distance from Earth. When you're 20 light minutes from Earth, you're not going to have a medical consult for the issue that you have going on. So you have to do autonomous operations, and you have to have in a 4-person crew, for instance, you will have to have somebody who can back up the flight surgeon, assuming that there's a flight surgeon on board, in case the flight surgeon is one that has a problem. You have to have instrumentation that's smart enough to be able to help the crew members do the work that needs to be done. So we are looking now at ways of trying to change station around so that we can start simulating deep space missions. And one of the things that we're looking at is extending the duration for more crew members. You probably are all aware of the one-year mission that we flew with Kelly and Kornienko a few years ago. That was a very good demonstration, but it was an N of 2. And if we want to try to understand how to extrapolate the countermeasures that we have for gravity and for eclipse systems to a 30-month mission, so you go from 6 months to 30 months, it's a very long stretch. If you can get some data, if we can get enough data at 12 months with enough subjects, then it makes the extrapolation something that's easier to do. The second thing we're trying to do, and I think Julie will talk a little more about this, is to be able to close off part of the station and increase the time delay, or include time delays, and isolate crew members for up to a month or two at a time on the station itself to begin simulating how we would do deep space missions, or to try and get some sense for the issues that might come up with people that are isolated and not getting the direct communication and having to work autonomously through problems.
Thanks, Bill. Alexei, пожалуйста.
Спасибо, добрый день всем.
Thank you. Good day,
По
everybody.
роду деятельности я занимаюсь медицинским обеспечением и участвую в медицинском обеспечении космических полетов.
Working in
Поэтому
medical
позвольте я буду говорить в этом направлении. Ну, как это было сказано предыдущим выступающим, мы
space
научились
missions. As it has already been said, we have learned how to fly for 6 months, for 12 months. Before that, Russia has already had experience of long duration flights of that
Уже
kind.
тоже неоднократно говорилось, что
And it has been
МКС
said here
является
before
уникальной
that the ISS is a
научно-исследовательской
unique
лабораторией. И
lab
вот
in
полеты,
space,
которые были осуществлены
and
за
the
этот
missions
период,
that we
пока
have
летает
had
МКС,
so far
позволили создать нам
on
достаточно
ISS
эффективную медицинскую систему медицинского обеспечения
provide
космических
interesting and a good sufficient
В
base
настоящее
for
время мы уже
medical support for
имеем
long duration flights.
эффективные и
We are talking about
надежные средства защиты
efficiency
организма
and
человека на всех этапах
safety
космического полета.
of
Это и на
human
этапе
beings in
старта,
space,
выведения,
at
на этапе
all
приземления
stages, launch,
экипажей космических.
docking and landing.
Тоже хорошо себя
We
зарекомендовавшаяся
already
система
have
профилактики
good systems
воздействия,
of
неблагоприятного воздействия факторов космического
countermeasures
полета на
for
человека.
space environment.
Наши космические
Presence,
экипажи
so humans in space
достаточно
environment.
хорошо обеспечены всеми ресурсами.
Our
Это касается воды, питания,
crews
одежды.
are well supplied
В полете
with everything
в настоящее
necessary,
время
that is
проводится
water,
эффективный медицинский
food,
контроль,
everything in
который позволяет
medical
оценить состояние
control
здоровья всех
and
космонавтов в течение всего
monitoring
полета
of all
и
crew
на
members
ответственных
is
этапах.
always
Когда,
present
допустим, космонавты
at all
выполняют
stages when
некорабельную
cosmonauts
деятельность
are
на
performing
этапе запуска, опять же,
extravehicular
и
activities,
посадки
for example.
экипажей. Но
We
сейчас мы говорим о
especially
том, что
attentive
подготовка
to
к
the condition
перспективным
we get
космическим
all
полетам
the
это
data in
полеты в
preparation
дальний
for
космос,
long
на
duration
Луну,
flights
на Марс.
to the
И
moon, to Mars.
наверняка
We are taking into account
все мы понимаем,
everything
что
that we have gathered
существующая
so far in
система
our
может быть
experience.
только основой
The current
для
system can
системы, которая
become
будет обеспечить
just the
человека в
basis
этих
of
полетах.
what
И
we are going to
мы
evolve
должны
into later.
вот в ходе вот этих
And
полетов, которые выполняются сейчас в
during
настоящее время,
the
конечно,
current flights,
предусмотреть
our task
те риски,
is
которые
to
возможны,
assess the possible
и с которыми
risks
столкнется человек, когда будет осуществлять
for
полеты в дальний космос.
further exploration.
Конечно, как уже здесь
Of
говорилось, это
course,
будет
as it has
большая
already been
длительность космических
said, it
полетов.
will be long duration flights,
Очень
isolated
резко
flights.
повышается роль
And
экипажа,
the
так
role
как
of the
часть
crew
или большая часть его
becomes
деятельности будет проводиться в
more
автономном
important
режиме.
because most of the
Уже
operations will
говорилось о
be
том,
run
что будет
exclusively
экипаж
by the crew
подвергаться
members.
воздействию более
Also,
сильной доз радиации.
radiation problem
Также наверняка будет
becomes
воздействие гипомагнитного
especially
поля, а может быть где-то
important.
на
Also,
каких-то
hypermagnetic
этапах полета
field.
будет и отсутствие магнитного поля.
Maybe there will be no magnetic field at some stages of the
Также
flight.
надо будет отрабатывать
We will have
элементы
to
медицинского
verify
обеспечения на
elements
этапах
of
посадки
medical
на другие
support
планеты и старты
for
с этих планет.
landing
Ну и, конечно,
other
инопланетная деятельность
planets
будет
and the launches
потребует
from other
совершенно
planets.
других подходов
There will be
к медицинскому
absolutely
обеспечению экипажа
different
в
support
ходе этой деятельности.
for the crew during
Поэтому,
this type of
как тут уже и говорится, и как
activities.
цель нашей
And this is the purpose of our panel. We have to use ISS as much as possible to resolve the problems that we foresee in the future as we venture to the flights for Mars and the Moon.
Julie, a few words, please.
Sure. So what I want to just say a couple of comments about is how the space station fits in our overall human spaceflight strategy and how that influences the way that we use it today. The beauty of the space station is in having a significant capability built by a partnership over several decades, you have the opportunity to respond to changes in economy, changes in geopolitics, and even changes in science. And to adapt to those, to have we have facilities on the ISS today that we would never have thought that kind of science was possible when the space station was built. We also have a partnership today that is able to extend far beyond just low Earth orbit and envision ways to work together across the entire human spaceflight endeavor. So that international partnership becomes one of the most important ways that we use the space station as our stepping stone to extend beyond low Earth orbit into the cislunar vicinity, and then eventually to Mars as a species and not just as a single nation. In low Earth orbit, we now envision something much different than we would have imagined 20 years ago. We now see that you don't get done doing science in low Earth orbit. In fact, the discoveries that we've made and the impacts that those results have had in the scientific literature paves the way for why you need a capability in low Earth orbit over the long term to continue to do research. In the same way, you never finish doing research in the marine environment. You never say, okay, we're done. We don't need any more ships to do research. You don't get done doing research in low Earth orbit scientifically. You also never get done doing research in low Earth orbit technologically, because each time we make an advance in technology, before we send that technology on a mission beyond Earth's gravitational field, we need to be sure that it's going to work for the time frame that we need. And finally, we need to be sure that our operations approaches are appropriate. So to maximize the use of the space station, we have to now view it in the context of our transition to future platforms in low Earth orbit, so that our science transitions smoothly between the many capabilities we have today and the capabilities that we need for the future. We also need to make sure that the way that we use it for exploration is synergistic across other spaceflight platforms, such as the Gateway and lunar surface operations. And so one of the really exciting things going on right now is thinking through, if you can do it in low Earth orbit, if you can do it on the space station today, you need to do it there, because you can't afford to do it in cislunar orbit. But how do we make sure that the research and the technologies we're testing there and the operations we're doing in low Earth orbit then smoothly transition to being able to do that subset of experiments you can only do at the Gateway, and that subset of experiments you need to do on the lunar surface, so that we are across all human spaceflight ready for Mars. And so some of the things we're working on is, how do we make Gateway utilization part of the overall human spaceflight endeavor, not something separate. It's really important, and I think people in this room have the opportunity to be thought leaders in thinking about, it's not about each platform taken in isolation. It's about the flow of scientific knowledge and the flow of technology across platforms, and that how we use the space station today has to be seen in that broader context. Thanks.
Thanks, Julie. Salajan, right next to Julie, please, a few words.
Да, добрый день, дорогие друзья.
Good day, dear friends.
Очень много сказано о будущем
It has been said a lot
МКС, и
about
то,
the
что
future of ISS.
если говорить по сегодняшний день,
And
то
if we talk
я
about
считаю,
today,
что задача
I believe that
МКС
the
выполнена.
task of
Но
ISS has been
мы
completed.
говорим о будущем
However,
и о
talking
будущих
about the
полетах
future, we are talking
на
about
Луну,
the
на Марс,
future
поэтому в
missions
дополнение,
to
вот что
the moon,
сказал
to
Алексей,
Mars. In addition to
хотел
what
бы
Alexei
добавить,
has mentioned, I
что
would like to add
выполняя научные
that
эксперименты,
while
мы
we are
не
performing
рассматриваем
scientific experiments,
чуть-чуть,
we sometimes
не видим свое будущее.
forget
Когда мы
about our future.
полетим
We're
на
not
Марс,
looking
то
ahead. When we go
всем понятно,
to
что
Mars,
мы не
everybody
сможем взять
understands
все
that we will
запасные
not be able to
части,
take all the
оборудование,
spares, all the
и
hardware.
если что
And,
случится на
if
полпути, то
something
у нас
happens
не будет
halfway
возможности
there, we will not have
срочного
a way
возвращения
to return
обратно на
to
Землю.
Earth
Поэтому
immediately.
МКС должна сейчас
That's why,
работать в том направлении,
ISS will
чтобы
have
создавать
to
вот такие,
concentrate efforts
создать
on,
такое оборудование внутри
creating
Международной космической
such
станции, чтобы
hardware
она могла
inside ISS
печатать,
it
делать
may,
это наподобие мастерской. И
build,
это у нас сейчас это реально. Например, вот 3D принтеры
like
появились,
3D
и мы
printers, for
могли
example.
бы
Those are
создавать
amazing. We
реальные
can use them for,
детали с реальными,
making,
с реальными
real
физическими
parts with real
характеристиками.
physical
И
properties that we
также
will
вам
need
известно,
to
наверное,
repair
что
something, repair our
в скором
systems
будущем
in space.
в российском сегменте
Obvious
появится
that on the Russian
3D
segment,
биопринтер,
we will have
правильно?
the 3D printer,
И
right?
вот это
Yes,
уже
on the
начало
Russian
того,
segment
что
we are going
мы
to have it. This is the
должны
beginning of
использовать
what we are supposed
МКС
to
для того,
use
чтобы
on
смотреть
ISS
дальше в будущее. И
in order to
МКС пролетает
prepared
еще,
for the future.
скажем,
ISS
еще 10 лет,
will
и
probably stay in
у
orbit
нас
for another
немного
10
времени
years,
для
so
того,
we don't
чтобы
have really
испытать
that
те
much time, but
технологии,
we have to
которые
use
будут
it
использоваться в будущем при полетах
effectively
к другим
for
планетам.
testing technologies in
Thank you,
preparation for future
Salajan.
flights.
Kate,
Yeah, so I think
we're hot swapping chairs here.
I think we're in an excellent place in terms of space station utilization. We've really maximized the space that's on station. We've maximized our crew time. And there's not a lot, we're really approaching asymptotic in terms of what we can get out of our current resources. So one thing I think we need to think about in the future is changing a little bit the way we do experiments. What I saw on space station was quite an awful lot of essentially shuttle mid-deck lockers, which is how we know how to build experiments in space, and this is great for things that need that size. But there are a lot of experiments. There's technology that's moved on that really can use things that are now into the microfluidic size. So, for example, when I was in grad school, not that many years ago, we needed nanograms of DNA to sequence DNA. We can now sequence DNA with even less than nanograms. We can do this with picograms. And when I was an undergrad, we needed micrograms. So we're moving about an order of magnitude every decade or so less. We're starting to see a lot of single-cell technologies come out of labs. So, for example, right now on space station, when we draw blood from astronauts or cosmonauts, we draw into a 7 milliliter tube. And that tube sometimes gets aliquoted, but it goes to 3 or 4 different experimenters. Whereas there are a lot of experiments these days that could be done with 100 microliters. So you could take that one 7 mil tube and you could distribute that to 700 different investigators. Part of the thing that we need to think about is what do we process in situ on board? Because as soon as you freeze most biological experiments, you lose that compartmentalization of information, so how things are segregated in separate cells. So we may need to do things like take blood, put it into a microfluidics chip that has antibodies on it that can separate out all of the different cell types, and then freeze those down into small microliter type containers or capillary tubes. I'd like to also encourage us to think about when we're planning an experiment, you've got your crew time for a crew to pipette. They get a couple things, they do 1 or 2 pipettes, and then they put something in the freezer. Well, if you're actually pipetting something with an 8-channel pipette or using some kind of robotic instrument, you could do this kind of thing into a 384-well plate. So with basically the same action, the same level of resource, which is crew time and some supplies, all of a sudden now you have 384 samples instead of your 1 sample or your 10 samples. So I think this is really the next big leap forward in space station utilization is how we use microfluidics, lab on a chip type samples, and how we increase the throughput of our sampling for the same level of resources 10, 100, or 1,000 times is really quite reasonable given current technology today.
Thanks, Kate. Let's open the floor up for questions. We need a floating microphone. Do we have a floating microphone around here? Oh, we do. Okay. And let me throw out the first grenade question, and I'm going to do it to someone that's good at handling grenades, and that's Shep. And this has to do with when we do, if we do split time delayed ops like Bill was talking about on station, it's going to make a couple people working on station sort of like it was when you were there with problematic conversations with the ground, so the crew's going to be working more autonomously. And I'm wondering what you think about in terms of utilization and efficiency with that group compared with the group that's chasing the standard red line.
Don, my comments were meant to basically separate out some of the operational aspects that have to do with the health and safety of the station as a whole rather than the science utilization. I think you could have an environment where you do both. I was just very, if you will, agitated when early in our flight, Houston and Soup could not agree on a single plan of the day, and this kept happening over and over again, and there was not a good realization up front that the station in its early days was one platform and it had to have one plan, and there was no cohesiveness on the ground about creating what that plan was going to be. When you get down to how you operate with docking, undocking, aborts, emergencies, casualties, things that are going to happen in space, and maybe we haven't seen a whole lot of them yet on space station, but they're out there. You have to operate in a little different environment than what I think station is configured for now, and that was my point.
Okay, questions. We've got a microphone. Raise your hand, get a microphone. Walt.
I think what we've seen is on the space station, they've developed amazing ability to extend survivability over long periods of time and developed hardware to do that. And I think it's been a terrific job. We ought to keep in mind that also can be an early development of the kind of things we need to survive for long periods of time on the lunar surface. I think we'll have a more or less permanent base or survival place up on the moon, and I think that we ought to be starting to look seriously at all that stuff from the space station as an advantage to it. I don't know, am I off base on that?
Anyone on the panel want to comment on that? Bonnie?
Yes, I just barely touched on some of the engineering topics, but engineering will allow the science to occur. And one of the areas we discussed last year was our lack of real understanding on mass and mass transport and chemical operations in fractional G environments, which are fundamental to a lot of the life support systems, habitat, heat, thermal models, as well as ISRU, and ISRU hasn't even really touched on that. So I really think we used to have in the plan a very large centrifuge that has, that went away. We have some small centrifuges that fly, but we really need to be thinking about some of the fundamentals of engineering development that occur in fractional G1, G, and 3HG environment, including life support systems, before we build them here and they don't work.
Thanks, Bonnie. Before we get to the next question, Shep had one follow-on
I wanted
comment.
to share one little vignette that happened a couple times in Expedition 1 I think is pertinent to the whole issue of how the station operations are organized. Before our flight, we had a meeting. Expedition 1 was in the Russian Space Agency. Chairman Koptev had his direct reports with the crew there, trying to assess if we were ready, the whole organization was ready to fly the first expedition. I went around the room. There were no real adverse comments, and I raised my hand and said to Mr. Koptev that the crew, Sergei Krikalev and Yuri Gudzenko, had not been issued their contracts for their flight. And this was causing undue stress on them that was affecting their readiness to complete their training and fly their mission. And in my view as a commander, this was unsatisfactory. And this was quite an interesting debate at that point in the Russian program, because this is not typically the role of a crewman to say such a thing. But I felt very strongly that not only should someone in the crew be responsible for keeping people safe, but also, their well-being. Are they being taken care of? And I feel, again, on an expeditionary mission that's going to be a long way from Earth, this has to be established. And if we don't, we're going to be poorer for it.
Thanks, Shep. Yes.
Yes. What do you see as the role of the space station in test and evaluation and ultimately optimizing use of energy management systems in space?
Anyone?
Well, as one of the few engineers, how many of us are there? Okay, I've got a few here. Absolutely. The station, as I mentioned, was also established as a test bed for engineering, for exploration and technologies. And it's a wonderful place to go. We also know that some of the environmental control and life support systems that pass all of the qualification tests in 1G don't always work in 0G. And will work again once they're returned to the Earth. So we have to use this really readily available test bed, our national lab, where we can't replicate that environment anywhere else, to the maximum use possible in energy management, communications, closing off laboratories to test latency in communications. It's a wonderful platform. It's international, and we have this unique opportunity to do so.
Well, I just want to pile on with Bonnie. I think if we're going to do anything expansive in space, we have to have advanced propulsion, and space station is the place to develop and test this.
And let me add, in the energy department, station has these solar panels, and there's about 100 kilowatts of power. And people can think that once you build your solar panels, that's free energy. Well, because of all the surface area of those solar panels, station loses 100 meters a day in altitude. And that means about once every 3 weeks, our Russian colleagues have to fire their rocket engines up and reboost station. So the cost of this free solar power on station actually comes from having to supply chemical propellant to station to keep it reboost. Yes?
Tell me, please, what is your opinion on using capabilities of ISS for performing of studies to the interests of exobiology, looking forward to lunar program realization? Now is in Russian experimental program is a real renaissance to this subject. So one experiment is finished, 2 experiments are ongoing, and 2 experiments are planned. And very interesting results were obtained, intermediate results. So viable colonies of spore-forming microorganisms were found and investigated on the surface of outer surface of ISS. To my opinion, we should use the remaining time of ISS activity for thorough investigations of this event, this subject. What's your opinion on this subject? Thank you.
This sounds like a Kate question to me.
Yes, I absolutely agree. I think we have a really unique opportunity both internally and externally to look at a spacecraft that's been separate from the planet for a number of years. So it's evolved its own environmental niche. So we do have plans right now to do an interior analysis of the space station microbiome with 1,000 samples. And that's going to be a very detailed temporal and spatial analysis. And this is really the way that you do a microbiome analysis. You can't take 3 samples and say you understand the microbiome. So we need to really look at the longitudinal analysis of what happens when different crews get up there, how stable the microbiome is, and what is a good example of an interior space station microbiome. I think we have one. We haven't had a lot of microbial problems, but we're going to want to know how to replicate that for a long duration journey and what our species diversity is. I think exterior station microbiome sampling is also incredibly interesting, and we have some early technologies in development to allow us to take the samples. I think our program is a little bit behind the Russian program, but this is very interesting. And I think looking forward to the moon is, for a little while, maybe wasn't incredibly interesting to biologists. I actually think this should be the #1 interesting place for biologists to go because it's the perfect negative control for Mars. So anything that you, just with your normal human lunar base or your spacewalk, as you go around your daily activities, if you sample, that's the catalog of the bioburden that we're bringing with us. And then we can decide from there, do we want to reduce that bioburden or do we just want to map it? But it's the first place that's really going to tell us what happens with human equipment and microbiomes in a completely sterile environment. We don't have a way to do that on Earth. We don't have places where there aren't microbes already present. So it's also sort of a fascinating, really big picture philosophy of when we do go to the moon and hopefully set up lunar bases there, this will be the opportunity over a number of decades to watch the first kind of microbial plantings on a planet. Whether or not we intend to do any kinds of terraforming activities, this will be the first time that we're really bringing a microbiome to a planetary surface. I think that's a unique opportunity that needs mapping and sampling from the very first human activities on the surface.
And I can add a little bit to that. We're learning every day more about the importance of the microbiome within us in terms of nutrition and adaptation to various drugs and uptake of various nutrients and pharmaceutical agents. we don't know very much at all about the interactions among people and their environment, so the humans that are aboard, especially in an isolated and confined environment, or how people will share their microbiomes with one another. So this is another area that riffing off of what Kate said, very important, and it's emerging. We're learning now on the ground some things that we didn't know when the station was built about the microbiome of the built environment and interactions between people in that environment, and it's really important, I think, for these missions that we're planning.
Next question, yes.
Я хочу сказать, что у нас есть прекрасный опыт выполнения совместных исследований по оценке здоровья организма после возвращения на Землю. Это наш эксперимент филд-тест, который проходил совместно между российскими и американскими учеными, и он дал нам уже возможность оценить состояние человека после длительного космического полета, что, конечно, нам очень важно, если мы готовимся к дальним миссиям. В этой связи хотелось бы продолжить такое же международное сотрудничество в области оценки состояния здоровья. И я думаю, что нам надо продумать какой-то, вот если действительно будет какая-то изолированная среда для людей, для космонавтов, астронавтов, имитирующих длительный полет, то, я думаю, надо предложить единую оценку состояния организма. То есть, к сожалению, у нас до сих пор на российском и американском сегменте происходит раздельная оценка состояния здоровья. Если мы думаем о совместной миссии, то мы должны сейчас идти, мы в течение 10 лет идем все ближе и ближе по системе профилактики. У нас с российской стороны космонавты используют тренажер ARED, что значительно увеличивает нашу работоспособность и укорачивает время адаптации к условиям Земли. С другой стороны, я знаю, что американские коллеги во многом после итогов эксперимента SPRINT пришли к протоколам близким к тем, которые применяли наши российские космонавты. В этой связи я думаю, что МКС, конечно же, прекрасная платформа именно для сближения наших усилий по профилактике гипогравитационных нарушений в организме человека. И я думаю, что стоит нам задуматься о совместных экспериментах именно на МКС по оценке состояния здоровья и по совместным программам по профилактике.
That deal with countermeasures and health monitoring of the crew.
So as Elena well knows, I agree with everything she just said. And one of the interesting things we had last week, we had a small workshop that was organized across the ISS International Partnership to talk about using ISS crews as better models for isolation and confinement, surface operations, and other aspects of a Mars mission. And one thing we talked about very specifically were the great successes of field test. And SHEP field test is an example of a fully integrated joint experiment with U.S. and Russian PIs, co-Is, and subjects across of that. All of our work in understanding the SANS issue, the vision issues, is another example of that, where we share all of our hardware and we test our hypotheses jointly. One of the things that in our survey of use cases of things that we can't do on ISS today, but we would like to be able to do to better pave the way for Mars missions, would be doing a field test that is amped up a level. So the great thing about field tests is we learn a huge amount right at the landing site in Kazakhstan. The limitation is we need to get out of Kazakhstan and back to Russian soil. So we're not able to do things 2 and 3 days post deconditioning that would really help us model on a Mars mission scenario. And in the Human Research Program, we worked with the Mars Capability Study team to look at what those first week scenarios are. And it's amazing to see your assumptions about what a crew member can do each hour after they land on Mars in a deconditioned state has massive effects on the mass of your Mars landers and the mission parameters. When you add to that your assumptions about planetary protection and what you have to do with the microbes, those two things together are the biggest drivers. So it's biology that is driving your Mars mission masses and your engineering scenarios. And there's a huge amount that we can do, I think, using deconditioned astronauts on ISS and bringing them back into more realistic mission scenarios and pushing that envelope. Because if they can successfully do EVAs at 3 days, Oleg tells me that GCTC's been doing some work in that area, what they can do at 3 days could make a huge difference in your scenario. What they could do at 12 hours could make a big difference. Can they control robots, or at least could half the crew do a contingency EVA to connect to power on a Mars landing, for example? All of those things become absolute mission design drivers, and those, the best way that we're going to be able to look at those is by using ISS in a smart way today.
Bill, you have anything to add?
Yeah, I think this is, I agree with everything that Julie said and that Elena said. This has been a very interesting experiment and a very challenging experiment from a scientific perspective. We have a scientist who actually goes out on the search and recovery choppers in Kazakhstan to the landing site and does studies in the tent right after crew members have landed. Now, long ago in the space station era, and when we had shuttle recovery for ISS, we got some early data on how crews were responding. This was looking in the field now at people coming back from 6-month missions using functional tests, and we're understanding really in the first few days how significant the differences are between a 6-month mission and a 2-week mission aboard station. We're able to protect bone, muscle, and cardiovascular function pretty well, but the vestibular function just swamps the response, and we don't have an adequate countermeasure for the vestibular function. This is now having implications for the new U.S. vehicles that'll be landing again in the water, or perhaps on the land, but the first ones that are starting on the water, about what assumptions you can make about a crew's ability to egress on their own once they get there. So the data have recently been presented to all the senior program managers for the landing vehicles that we're developing now, so that they would be aware of this, and of course the medical side is trying to figure out what their strategy will be for getting crews out of the capsules once we've landed. The other thing is, and Julie sort of alluded to this, we are starting to look not just at individual performance, but at trying to look at the performance of a team. So if you have 4 crew members that are landing on Mars, you may have one that is very debilitated because of whatever issues. But if you have another one that can help that one, or can do that one's job, then your probability of success is going to be higher. So we're now starting to look not just at individual statistics, in our scientific data, but on how a team would respond, and what the probability is of having 4 crew members who are really debilitated versus having 1 or 2. So we're looking at all these data, and this came from this joint work we've been doing with the Russians for the past 5 or 6 years now, 4 or 5 years.
Yes.
Well, I'm going to ask a question about food and nutrition. We have grown plants a long time in spaceflight, and now on ISS, some nice breakthroughs in growing plants, and hopefully be able to do more of that. Obviously, the ISS gives us a good platform to begin to be a little more self-sufficient with food, and not having to use basically the kinds of foods we used in the Mir and Space Shuttle program, and having some advances there. So the question, maybe Julia and Bill are the right people. How do we move out of these little demonstration projects, which are wonderful? I love them. But we need to move to more self-sufficiency in food, and it seems to me that the beginnings of the breakthrough technologies are there. And certainly on the Mir, the Russians were able to raise quite a bit of food. So I'd like to see what is going on in terms of getting us out of the thermostabilized freeze-dried food into having more self-sufficiency, which we will need for Mars, and certainly the Moon would be a good platform.
Yeah, one of the really interesting things about food is how much it's a driver in terms of volume. And what's interesting is the engineering trade between a biological system for growing food that could be a little dodgy in microgravity, because we still have not gotten really confident that we could grow CRIT-1 food supplies that we needed to eat on a long duration mission, because we get funguses, we have roots flood out, we have a number of problems that are not well solved yet. So we're still in the demonstration phase. But if you start thinking about Crit 1 fresh food that you're growing on the way to Mars, there's an engineering trade between that and freezers that is not well resolved. And right now, the Mars study team, for the same reason that they avoid bioregen life support, because microbes don't always do what the engineers want them to, and they focus on chemical life support, is for the same reason some of the Mars capability study team models are imagining massive banks of freezers rather than banks of plants. And that's partly because our plant biologists really need access to space station to improve that next generation of technologies, and they're working on it.
And I think we're working closely with the space biology folks who have been developing plant systems for growth in space. And we're actually looking at some things that might fly on Gateway, something called the Gateway Garden. That would be a full-up demonstration of our ability to grow crops that could be, it'll probably almost inevitably be a supplement to the other food that we send. Food is going to be one of the critical issues. Actually, it's one of the red risks that I'm working on. It's a very hard thing to do for 30 months. We're looking at creative approaches, and Shalazan mentioned a few minutes ago 3D printing. We're looking at the potential for 3D printing food, also pharmaceuticals perhaps, and not just technical engineering things, and for 3D printing medical instruments. So if you need a catheter, can you 3D print the catheter when you need it, and then recycle it and 3D print something else? But back to food, another important issue in distance from Earth and isolation and confinement are the psychosocial and behavioral issues. And when you're away for 3 months and you realize that every culture on the planet celebrates special events with specialized food. How do we prepare? And we know we already do this on station when we have special festivals that special food gets shipped up. But how do we provide for that to maintain the esprit de corps for the crew members when different events in their calendar come up during these missions that are going to be so long lived? So this is a very important area, and we don't have a really good handle on how we're going to do it all yet.
Yes. Microphone. Oh, okay. Next up. Go ahead.
So I say this as a clinical trialist with all deference to ethics and all the issues thereof. So we have a situation where each astronaut has a tailored countermeasure plan. Maybe they take ACE inhibitors if their framing having risk score is above X and such, and this is based on mostly faulty anecdotal Earth-based data without good clinical trial evidence for healthy people. We have the various different resistance training used by different countries, different physical training. We have the different readaptation to gravity programs used by different countries. It seems, as a clinical trialist, as an opportunity to do randomized crossover design studies to find optimal medical management strategies, optimal countermeasure, optimal rehabilitation strategies. Is this something that we could do? It's hard, obviously, and there's tremendous ethics issues. Is someone even able to volunteer for a thing like this or sign as informed consent even an issue? But is this something we could do with, now a lot of the new quick lab on a chip outcomes that we can study rapidly with biomarkers to try to get better at how to manage spaceflight?
So if I understand it, just your question, one thing I look at is the forcing function for the reason we have the countermeasures we have, right? So we live in a small N world. Hundreds of people have flown in space, but the numbers that have actually taken part in the really good data-driven experiments are small, in 8 to 12. So the hundreds of people does not give us a big N world. And so you really have to choose carefully where that data set came from. That it was a Skylab data, was it station data? Was it station data before 2009 or after 2009? That was an inflection point in our countermeasures and food system and everything. So to really do the studies you're talking about, you would have to do it in the context of the vehicle and the program. And to have it have meaning, it will only have meaning if you have the identical program. You won't have the countermeasure suite we have on station when you're on your way to Mars. So what I would say, probably looking at is doing more studies on the systems than the individuals. I think I'll speak a little bit for some of the other astronauts here. We're in a pretty good envelope right now. We bring people home pretty strong and pretty fit, especially compared to what we used to. So you could say we're good enough. It's time now to test the next system that's going to be forced on us by the next program. So I think that's probably a direction we're going in looking at new, smaller, compact, resistive exercise devices and whatnot. I think that's more the focus of our study than trying to optimize health for the individual.
Yeah, so I think this is a really good point, is that we have a lot of different modalities and we're not really crossing people over. I think one of the reasons is that they work. And so now we do get into an ethical issue of if we have something that we know works really well for bone loss, should we accept something less? I think what we haven't done, the current studies all essentially have one endpoint, and that's when the crew member returns, and there's a variety of different tests, and we're looking at DEXA in a couple different ways and also kind of more volumetric studies. But what we haven't done is taken advantage of the time course data while the crew member is on board. And so we actually could probably get ourselves a lot more data points about the course of bone loss and progression if we monitored this real time in vivo on board and probably through some kind of biomarker study. If we started collecting that data, then every single crew member turns into now 50 data points. And so you could design a study where they're, probably even the best ethical scenario, ARED breaks every now and then. So you just take advantage of the ARED break and you sample during nominal ARED, and then you sample during when ARED is down and you're not exercising. Or you could probably have people, cross over, be off ARED, be on Russian exercise equipment, be no exercise, be treadmill only, be rowing only for a week or two and sample them. And if you have the sensitivity in your biomarkers to predict a certain level of bone loss, you don't have to go all the way to the endpoint and put that crew member at risk when they're back for not having enough bone. You just see what it does to the levels, and does it increase or decreasing your steady state levels of bone turnover.
Just quickly add one thing about you mentioned about the partnering countries, and we are definitely working together with the NASA, Russia, and Canada, Europe, and there's a lot of the new protocol coming up, like sprint protocol, the pressurized training protocol, and that's coming up with the data sharing efforts to make sure that all those data, new trial is they're shared across the board and come up with the new plan. So we are definitely we are part of the new studies.
So I still have a hard time with the concept of extrapolating from a 1-year mission to what will be essentially a 3-year mission. Can we really safely conclude, if nothing happens after 1 year, that we will see nothing in like an adverse effect during a longer mission? And I guess the best example is what was called VIP, what is now called SANS. That is something that really only came up once astronauts spent half a year on the ISS, and that we really hadn't seen, at least not to that extent, during the shuttle missions. So, the unique thing about the ISS is that we have microgravity there. Although we have analogs on the ground, they're imperfect. So really, shouldn't we use the ISS with the microgravity environment to really put at least one man and one woman up there for 3 years before we dare sending a real crew to Mars? That is my question in terms of utilization or good utilization of the space station.
So let me just, I'm not going to answer your question, but can I just bend it a little bit? Because I know we've considered sending people up there for the time that would be representative of deep space crews, returning them, doing Mars analog type things, shooting back to station for return. If you're going to go to all that trouble, we have discussed that. So can we put that on the table as part of your question as well? Because 3 years in microgravity, we would never do that in any of our DRMs, any of our design reference missions.
Let me just pile on. I do believe we are not ready in terms of crew cohesiveness and the ability to stay functional psychologically for that extent of time. We're not there yet. We don't know how to do that.
But what you do is you use a menu of different analogs across human spaceflight platforms. So a 1-year mission is your worst case for a Mars transit. Then as we start moving to lunar surface ops, we can start using that as an analog for Mars surface ops, although it's an inadequate analog because you've got a different gravity level, but you use each of those tools along the way. We have to talk about, do we need model organisms? Do we need animals at 1.6G? to help us make the translation from the things that we've learned in microgravity and so forth. And so what we wind up having to do is use every analog we've got, from Antarctic field stations where we're studying confinement and behavior, through things like Hera, where we've got a very controlled environment at Johnson Space Center with crews going through it. Then we use our gravity analogs, which today is the space station for microgravity, but will also then include Gateway and lunar surface. And then we have to put together all of those pieces with endpoints we know and with a reasonable sample size. And we have to be really creative in using every subject in every unique circumstance. We can't randomize it, do a full randomized control study because we are at small n, but we can work across all of those platforms to feel like we have a pretty good picture. And then the other thing we've got to talk about is, do we need to do a shakedown mission? Before, whether that mission is a low Earth orbit station-based mission or whether it's actually a shakedown of the full technology for Mars transit and the full mission architecture, I would say the engineers would like to have it be the second one of those. You have some advantages to doing both so that you get some experience ahead of time. And so it may yet be that right towards the end, when space station is getting ready to transition, or perhaps in one of the commercial partnerships that low Earth orbit should transition to, that one of those would be the source of some kind of a Mars simulation, full up 2-year study or 3-year study.
But now I'll answer your question. So I absolutely agree with Julie. You've got to piece everything together, but we need probably a different mindset. We're not just learning about people in space on station. We're learning how to learn about people in space. And there's a learn-as-you-go mindset that fueled the Apollo program. Otherwise, they may never have gone because they wouldn't have satisfied everybody's full-up analog experience or what have you. We're learning that there are some tools that we're going to need on the road to characterize the next VIP, Mach, SOS, SANS, or whatever you want to call it now, that appears on Mars that we had not anticipated. So, what some people call a failure of imagination, I just call it discovery, and you need to be ready for it. So having the tools to learn how to learn, to do point analysis and return results to the Earth rather than long-term sample analysis, that's another thing we're getting out of station. And to me, that makes us ready to go probably sooner than other people would think. So, just a thought.
Yes, please.
好，你好，我来自于中国。那么根据中国最近几年的发展呢，中国不仅这个注重于太空技术的开发，而且呢很注重生命科学的研究。我的问题是2个，一个呢，根据宇航员的经验呢，太空技术对这个生命的影响，就有哪些经验？这是一。第二呢，根据宇航员的体会呢，哪一些太空技术呢，将来可用于对人类健康方面的研究？
I come from China, and now China pays attention to the research of space technology as well as the research of life science. And I have 2 questions. Number 1 is, what do you think are the major physical exchanges of space explorers which we can learn to benefit lives on Earth? And what can we benefit the life science research on Earth?
So I'll take that a little bit, because on the space station we've been doing a number of surveys of the research that's been done so far, over 2,000 experiments and their scientific results. And even Chinese scientists have flown some experiments on the space station because we partner so broadly that over 106 countries have flown experiments so far. One of the interesting examples of the interface between fundamental science and the applied science we've been talking about so far is the area of bone. So early in human spaceflight, we saw bone loss as a significant problem, but now using our space station experience and multiple generations of countermeasure hardware and countermeasure testing, we now know how to keep astronauts from losing significant bone. We're down to worrying about some fracture risks on planetary surfaces and some other details. But we've solved operationally the bone problem from a human spaceflight perspective. However, the ability of using microgravity and its effects on bone to benefit us here on Earth is just beginning to be tapped. So we have a number of pharmaceutical companies that are flying animals to the space station, flying cellular studies, and using that to understand the mechanism of bone remodeling in people so that that can then influence medical care back here on Earth. So we come back to the fact that microgravity in low Earth orbit gives us a way to do controlled experiments we can't do anywhere else. And by taking advantage of those perturbations on living systems, we have the ability to make discovery about a variety of systems. Some others I see coming on the horizon are immune function, which is an extraordinary black box with very complex interactions, and being able to push on something in an unusual way in that black box has great discovery potential. Also, in terms of understanding microbial communities and the formation of biofilms is an area that's having great application. And the biomolecular properties, crystallization, the possibility of getting structures of proteins is another area with a lot of Earth application. You know, our Japanese colleagues, there's a company now called PeptiDream that is fully commercially flying as many proteins as they can for as many companies as possible to the space station every launch. So we see a number of these different applications, and those become the foundation of why we keep needing low Earth orbit over the long term. From a NASA applied science perspective, it's really good we'll have it because we're going to keep having things we need to test, whether it's the next generation of exercise hardware, such as the Atlas that's now small. We still want to test that and be sure that it's going to work and meet our needs for future missions. But at the same time, there's extraordinary room for basic science to have applications that make life better here on Earth.
And I believe you had two questions. What the second question?
What aspects could we learn from the space technology that can benefit the life science on Earth?
Okay, I'll repeat the question. What aspects of life science technology can we learn to benefit people on Earth?
So I can share my opinion on that as well. One thing is our ability to function in a closed-loop life support system has driven us technologically to make all kinds of advances. So, for example, a filtration system that was developed for an early plant habitat just to remove ethylene turns out to be really great at removing anthrax spores from mail handling facilities and removing viruses from the atmosphere in daycare centers and in elder care facilities. So we've seen a number of technologies that spin off from human spaceflight because we're driven to do something smaller, something more efficient, or something more effective by these extreme environments.
That last question is the perfect lead into what I wanted to raise. The United Nations has, under Unispace Plus 50 in the past year, focused on the question of populating how space can support the sustainable world. They have 17 different parameters which have been collected together by the summits on sustainable world. It strikes me that the full range of interesting material that has been presented by this panel should really be uploaded onto the platforms that either exist at the moment through ESA or perhaps through this organization, so that what we are hearing here can be shared and can gather the support on a global basis. So I do recommend that some consideration be given by either agencies, the organization, the International Space Medicine Summit, or the use of the ESA platform, which will be supporting this in the future.
Yeah, I'm not sure whether every session is being recorded for posterity. It is. George is nodding his head yes. So at least the recordings are being made, and I bet that folks here at the Baker Institute can make that happen.
But I'd like to add a few words about the way that the ISS partnership has worked with the UN. So UN-USA has a human space technology initiative, and the ISS partnership supported a series of meetings. Also, the Human Research Program sent space medicine experts, and there were a series of workshops at the World Health Organization. So I think all of the partners have been very active in trying to make sure that these stories translate across, and those were actually part of the Unispace body of evidence that was reviewed as the work that had been done across that. So one of the interesting things about the UN is I think some of my other space agency colleagues who were involved in this would probably share this. Even being at space agencies and in government agencies, we were blown away by the bureaucracy of the United Nations a little bit. And that's really saying something. But that said, when Unispace got together and when we saw those things feeding through, we did see that an effort that took over 7 years of space agency interactions, but we were able to feed some of those stories forward. And the ISS Benefits for Humanity, which is currently being reviewed and coming out in its 3rd edition across the entire ISS partnership. So US, Russia, Japan, Canada, and Europe all contribute to that. And those are directly fed in. I just had a conversation with Simona De Pipo, for example, who's the head of UNUSA right now, about how she would take advantage of that publication as it becomes available in December.
Yeah, I'm sorry. Yeah, well, we are definitely part of the UN discussions. The Human Space Technology Initiative, which Julie mentioned, this used to be managed by our former astronaut Takao Doi, and maybe your friend Chiaki is heavily involved in this UN Unispace 50. So yeah, we know what they're discussing, and we're trying to convey our opinion to them. Thanks so much.
Thank you. What is the right balance of basic science versus operational research for the remaining lifetime of the International Space Station?
That's a hand grenade question if I've ever seen one.
So
I'll leave it to the panel here because they can handle hand grenades.
There's a very gray area between what you mean as basic science and what you mean as operational science. When we start answering hard questions, we, from a human research perspective, that's predominantly applied science. We sometimes get to an endpoint that says we need to understand more about mechanisms. And we need to understand what's going on at a deeper level, and so we reach out to the applied scientists, and we cross over that the line that you are proposing exists. I don't think it really exists. I think so. For instance, in this VIP SANS, we really need to understand something about microcirculation. We need to understand something about the way that blood flow and lymphatic flow is regulated in the brain, and we're not going to do that at an operational level. We're going to have to get down into some animal models and/or some very directed studies in clinical environments. We're looking at how to use the microbiome, which and what the implications are of the microbiome on the immune system and on the ability to uptake various nutrients, as I mentioned before. So that interacts with the basic science. So there's a continuum of studies that go on, and I don't think there's any specific recipe for what the right balance is. I think it depends on the agency. So our program gets some priority on the station right now because we have ultimate aspirations to go to Mars, and we want to answer the questions that are relevant to going to Mars. But we don't get the full amount of crew time that are available. There's a whole bunch of other questions that need to be answered aboard ISS that are very important to understanding terrestrial medicine or terrestrial health or biology or physics on Earth.
I think that the framing of basic versus applied science has led us as a society to make some pretty horrible policy mistakes and as scientists, we've made the mistake of not communicating with our policy stakeholders that there is a continuum, that there is no
ultimately perfectly fundamental experiment, and there is no ultimately perfectly applied experiment. To use examples from the space station, we've had work that was selected just for its application to astronaut health that wound up making a huge fundamental contribution and didn't make any significant impact on the way we managed astronaut health. And we've had the reverse happen, where something was selected thinking this was such a fundamental experiment, and it transformed the way we thought about applied work. I think that human spaceflight is expensive and it's challenging, and our stakeholders tend to expect us to have some kind of application, but they're very willing for that to be an application to health on Earth or an application to future exploration. I think we can make the case for both of those applied aspects, and our stakeholders are willing and have different opinions at different points in time about those things. But underneath it all, you have to recognize that discovery is something that happens when you go into extreme environments and make space for that. Fortunately, basic science almost always has a relevance. The National Science Foundation, which in the US is the organization that funds and selects most of the basic science, they have relevant statements in every proposal they receive. So there is no such thing as basic science that you do in this extreme environment only for fun, only because you wonder what's going to happen. You actually have applied reasons, and it connects to the physics or the life science or something about that extreme environment.
I would just add one last thing, is that science is not the only place you learn stuff. You learn stuff in operations as well, and they're very tightly intertwined. And what we thought about, say, neuro-ophthalmic system is very different from what we think now. But what we think about environmental control life support system is also very different. We've found that sensitivity to carbon dioxide, for instance, seems to differ in spaceflight than it does on the ground. Now we're looking at technologies that scrub CO2 to a much lower level than we ever would have thought we needed. That's kind of an operational finding that we didn't necessarily anticipate. We've had some other embarrassing operational findings where our water reclamation system didn't account for the large debt of calcium and phosphate that people just pee out in space. Mm-hmm. The biologists knew it, the engineers didn't. So all of these things shift that line periodically, and so you have to emphasize where those new discoveries put you in a bind.
Well, we've reached a little past our normal date. Let's take one more question right here and then take a break.
So just a quick return to the discussion of the biome and what seems to me to be very compelling reason to go back to the moon, because it isn't there. And it seems as though, from being a former PI in the fundamental physics program, there was a proposal by another PI to use the moon, because it's so seismically quiet, to be an extremely good fundamental particle detector, and kind of like the AMS, but a much more capable version of it. So again, this concept of the moon as a null seems really compelling. But one question, back in 2005 at Ames, we had a big time when they convened all the fundamental physics PIs, and they asked us about the possibility of creating an artificial magnetosphere for long-duration space flight to protect crews from radiation. Is that still at a forefront consideration for, say, long-duration space flight travel to Mars, or are there other solutions that are being sought after first for radiation exposure?
This is not the radiation panel, and I know there's radiation people in the back, so I'll feel a little gun-shy, but I was part of a program where we looked at basically throwing, if you had it as part of a nuclear electric propulsion, what type of energy field would you need to provide what type of protection? And I can tell you that as of 2010 or so, we found that we could protect from a certain fluence of solar particle events if you had 10 megawatts of power. But GCR, which is our real big enemy for long duration cancer risk and whatnot, we just couldn't handle those energies. It's incredibly power intensive, and we're also finding out that the risk of solar particle events might be a little bit higher than when we calculated at that time. So I think it's Right. I mean, so it's in the tens of kilowatts you can probably protect, but we're still a long way from Star Trek shields.
Yeah. With that, let's close this session, and I'll make a comment that if you've got 10 megawatts of power on your spacecraft, that's a lot. And I could see Captain Kirk calling to Scotty to say, divert all power to the shields.
Yeah, but then you're at Mars in 6 weeks, and you're not so worried about it. So.
So with that, let's all take a break, and we'll come back here after the break.